Okay, welcome back everyone. Last chapter in the program is gravitational waves. So that was another important prediction of general relativity, which until now hasn't verified directly, although there's very good indirect evidence that gravitational waves indeed do exist. I mentioned this already in the very first lecture at the beginning of this course, that we observe binary pulsars which lose energy. And this is interpreted as evidence for gravitational waves. So the idea is that this energy is radiated away in form of gravitational waves. It gave a Nobel Prize for this, for Hulse and Taylor. But until now, there's no detector which has really registered an electromagnetic wave, in the sense that it says click and we know, aha, now here a gravitational wave has arrived. Okay, so what we want to do here is, of course, we want to discuss the theory behind gravitational waves. So this will be chapter 7. So gravitational waves have been predicted by Einstein in 1916, immediately after he had found his field equation. And he based this prediction on the linearized field equation. So on the theory where you do not work with a full nonlinear Einstein equation, but rather with a linearized version. Of course, this spoils a lot of the qualitative features. So if you do this, if you linearize the field equation and then discuss waves in this theory, you will see, and we will do this today, you will see that then the theory is very, very similar to electromagnetic waves. There are a few differences, but basically it's very similar. But this is really a result of the linearization. If you work with a full nonlinear theory, then gravitational waves are completely different. You should be aware of this. So what we are doing now is just an approximation which holds for weak gravitational waves. So that's the assumption which is behind linearization, that the amplitudes are small. If this is satisfied, then the results are quantitatively good. But one should be aware of the fact that the full theory of gravitational waves, the full conceptual understanding of it, actually should be based on the full nonlinear theory. And this is completely different. So because of the nonlinearity, for instance, the superposition principle wouldn't hold, right? Here in the linear theory, we would see you can consider a plane harmonic wave solution, and then you can superimpose them in the same way as you do it for electromagnetic waves. For the full theory, this doesn't work. If you have two solutions and you add them together, you get something which is no longer a solution. Yeah? So the solution as a superposition principle doesn't hold. This spoils the whole theory of Fourier expansions, for instance. Yeah? You can Fourier expand any field, but if the individual Fourier mode solves your equation, it doesn't tell you anything about the full series. So this will not solve the equation. So many methods which you are familiar with from linear theory actually do not work for the full nonlinear theory. So maybe I will make a few remarks about the nonlinear theory, where we get wave-like solutions really of the full nonlinear equations at the end of this chapter, as there's time enough. But the main part of this will be based on the linearized field equation. So I begin with the linearization of Einstein's field equation. We will then see that this gives a wave equation, and we can solve this wave equation with essentially the same methods we are familiar with from electrodynamics. Okay, so what do we mean when we talk about linearization of Einstein's field equation? We assume that we have a metric which describes our gravitational field, g mu nu, but this g mu nu should be close to the Minkowski metric. So if we had this in a certain coordinate system, then we would do special relativity. There would be no gravitational field, right? And now we assume that there's a contribution, but that this contribution is small. So what we will do actually, what's the mathematical procedure that we follow when we do the linearization of Einstein's field equation, is that we linearize all expressions with respect to the h mu nu and with respect to the derivatives. So in physical terms, this means that we get a theory which is a good approximation as long as these terms are small and their derivatives are small. Sometimes people forget to talk about the derivatives. Actually, that's not automatically satisfied, right? If a quantity is small, its derivatives could still be arbitrarily large. Yeah? You can have in an arbitrarily small interval, you can have a function which goes up and down very rapidly with an arbitrarily steep descent, right? So the derivatives could be arbitrarily large, even if a quantity is small. So what we do is actually we really linearize with respect to the h mu and their derivatives. So we assume both are small. So the idea that's the program, linearize all expressions which will occur. So in particular, the expressions which occur in Einstein's field equations with respect to h mu nu and their derivatives. So in the following, I will say that a quantity is small or first order if it is a linear expression in terms of h mu nu or its derivatives. So if a quantity is small or first order in this terminology, then this means that we can neglect quadratic and higher order terms in this expression. So that's a program we want to do. So we have a metric which is approximately Minkowski metric with a perturbation which is so small that we can linearize with respect to this perturbation. And we will then, in the next section, apply this for the case where this is wave-like, right? So then we have Minkowski space and on Minkowski space ripples which describe a gravitational wave. But for the time being, h mu nu could be anything. So this would, for instance, also be valid for the field of a spherically symmetric body, which we discussed in the last lecture, is far away from the body. Yeah, far away from the body, this would be a good approximation for the gravitational field of a star or whatever. So, of course, this can hold only in particular coordinate systems, right? When we assume that an equation of this form holds, then we restrict to a subclass of coordinate systems. We are no longer free to make arbitrary coordinate transformations. And it can be clearly said what sort of coordinate transformations are still allowed, where we know precisely what coordinate transformations are allowed that preserve this here. These are the Lorentz transformations, or the Poincaré transformations, if we allow also for a shift of the origin. And now we can add something to the Poincaré transformations, which are small of the first order. So that preserves the smallness condition. So coordinates are now fixed. Up to what? Up to transformations of the following form. We could transform our x mu in new coordinates, which are well, let's begin with a shift of the origin. Then let's make a Lorentz transformation. X nu. Yeah, where lambda mu nu is a Lorentz transformation. This means lambda mu nu lambda sigma tau eta mu sigma is eta nu tau. Yeah, that's a constant matrix. It's not x-dependent. So this whole expression is linear. And then we are still free to add a function f mu of x, where f mu of x is small of first order. Meaning it is a linear combination of the h mu nu's and their first derivatives, or higher order derivatives. I think higher order derivatives will not occur, so we could restrict to first order derivatives. Okay, so in this restricted formalism, we are now, well, now the gravitational field looks like a field in Minkowski space, right? So we have underlying our Minkowski metric and then a field on this Minkowski space. So in this approximation formalism, gravitational fields are like all other fields, like electromagnetic fields or whatever else you have. So in a sense, it spoils the whole geometric framework. But it is a good approximation formalism for calculations, and it has a lot of applications. For instance, the standard theory of weak gravitational waves is completely covered by this formalism. So we will now work in this formalism. So as we have now this underlying Minkowski metric, it will be convenient to use this for raising and lowering indices. So usually we use this metric, but now let's agree that in this chapter we use, so in this chapter we use eta mu nu and eta mu nu for raising and lowering indices. So we can then calculate how the inverse metric, the G with the upper indices, looks in this formalism. And my claim is that the G with the upper indices, G rho sigma, is eta rho sigma as leading order term. That's no surprise. And I claim that I get, with a minus sign, now the H with the raised indices, where the indices on the H are raised with the eta. And yeah, we can quickly prove this. And the proof is quite simple. So what we have to show is that this matrix is inverse to this matrix, right? That's what we have to prove in our approximation scheme. So we have to prove that if I take this expression and the summation index is sigma, so let's write eta sigma tau plus eta sigma tau, that this gives a Kronecker delta. Yeah? So that this is really the inverse matrix of this here. Well, let's quickly calculate this. Okay, let's write it term by term. Eta rho sigma tau, what's this times this? Then this times this, minus eta rho sigma tau. And this times this, eta rho sigma tau. And then I get a term which is quadratic in the H's. And our program is that we neglect these terms, so I don't write this. Yeah? We neglect all terms which are quadratic or higher order in the etas and its derivatives. And well, now what is this here? That's Kronecker, right? That's the inverse matrix of this here, so I get Kronecker delta rho tau. This here, here's the index sigma is pulled down with a eta, so I get H rho tau. And here, the index sigma is also pulled down with a tau, so I get H rho tau. So you see the second and the third term cancel, and I end up with delta rho tau in our approximation scheme. So this is indeed the inverse matrix. So that's the inverse of this here. Okay, and what we have to do now is we have to insert this expression for the metric into the left-hand side of Einstein's field equation and see what happens to the field equation if we linearize with respect to the H. So what is on the left-hand side of Einstein's field equation is a Ricci tensor, right? In order to calculate the Ricci tensor, we need the Christoffel symbols. So the Christoffel symbols can be formed from the metric and its inverse. So our first task is to calculate the Christoffel symbols. Don't worry, this will not be so bad as the calculation we did yesterday. So today the calculations will be not so long. So actually the first thing we have to do is we calculate the Christoffel symbols. So what's the general expression, just to remind you of the Christoffel symbols? So we have gamma rho sigma tau was 1/2 G rho and a summation index, let's say mu, and then the three terms with the derivatives of the G's. Okay, the summation index is mu. This is here it's a G, here it's a G, and here it's a derivative. You can easily keep it in mind if you remember the symmetry. You have two terms with a plus and one with a minus, and because of the symmetry, of course, the index must be at the derivative with a term with a minus sign, right? Otherwise, you would spoil the symmetry in sigma and tau. And now I distribute the indices sigma and tau on the remaining places. So that's a general expression for the Christoffel symbols. And now we insert our special ansatz for the metric here. Let me begin with a bracket. So the G is eta plus H, right? And eta, of course, is a constant. Yeah, it has the entries 1 and -1 on the diagonal and otherwise 0. So all components of eta are constant. So I get here only the derivative of H plus d tau H mu sigma minus d mu H sigma tau. And now this G here is this here. So you see it begins with an eta. So I have 1/2 eta rho mu. And then comes an H. So this H is then multiplied with these three terms. So this is already quadratic, and we drop it. Yeah? We don't keep quadratic or higher order terms. So that's all we have to calculate. That's the expression for the Christoffel symbols in our approximation. And now the Ricci tensor. Is what? So we want to calculate R mu nu. So this gives 4 terms. Minus. The first 2 terms have derivatives of gamma. So this will be your first order, right? If I have the derivative of these terms, then it's still first order in H. And then come 2 terms which are quadratic in gamma, products of gammas. But they would be already quadratic, so I don't write them. Yeah? So we only have these 2 terms. And what are the indices? The indices are rho, rho. Here I have the summation index here, mu, nu. And then I symmetrize, wait a minute, I symmetrize this expression with respect to these 2 indices, anti-symmetrize, sorry. The Riemann tensor is anti-symmetric in this pair of indices, and this is a contraction of the Riemann tensor, right? So I have here rho, mu, nu. I didn't want to write the indices underneath each other, so I should do it this way. So that's the expression. And we can read this from the line above. So I get 1/2. So this is rho, rho, nu. What do I have to do? I have to make the sigma into a rho and the tau into a nu. Maybe I could make a tau out of this. Then it's easier to read it from the expression above, right? So then I have exactly this expression here, where I have have to write rho for sigma. So I get 1/2 eta rho mu, and then partial derivative of what? This expression now with rho replacing sigma. So I have partial rho, h mu nu, d tau, h mu rho minus d mu, h rho tau. So that's the first term. That's this here. And the other term results from interchanging the lower indices rho and mu. So I get minus, actually I can write this here, right? Yes, I can write this here. Minus the term where the indices rho and mu are interchanged. D mu, oh no, sorry, I cannot write this in this way, nonsense, because I have the derivative rho outside, right? So I have to write it in this way. So and now I interchange here in this expression rho and mu. D mu h rho nu, d tau h rho mu minus d rho h mu tau. Okay, let's see. So let's compare these 2 terms. I think that's, no, it's not. Let me write it term by term. So I have eta, let's do it slowly, d mu, d rho, h mu nu. I have a little bit, why do I have 3 indices mu? Wait a minute, there's something wrong. There's something wrong. Yes, I have here a summation index mu, so I should not call this index mu again, sorry for this. You see I have 3 mu's, usual mistake. I have an index used for this equation and I use the same index here, so we have to rename this index. So let's call this, what, lambda. It's lambda. It's lambda. So the summation index, I've mixed up everything now, very bad. So rho mu, I want to leave this. This here becomes a lambda. This becomes a lambda. And here, the rho mu, this mu becomes a lambda. I hope that's correct now. So rho tau. Oh, and the nu is a tau, right? The nu is a tau. Tau. And nu is a tau. That's an awful game with indices always. Let me see. Lambda. Yes. I think there's a good chance this is correct. No. Let's see. So this becomes a lambda mu tau. That's the first term. And the second term plus eta rho mu d lambda d tau h mu rho minus eta rho mu d lambda d mu h rho tau minus eta rho mu d rho d lambda h rho tau minus eta rho mu d rho d tau h rho lambda plus eta rho mu d I have two rows down here. What is this? My goodness. I have to interchange rho and lambda. Rho and lambda. This rho is mu. No, this rho is a mu. So the first three terms are correct, I hope. And this was wrong again. So I have minus eta rho mu rho d lambda h mu tau minus eta rho mu d rho d tau h mu lambda plus eta rho mu d rho d mu h lambda tau. And now we recognize some good old friends. Namely, we recognize that such expressions occur. Remember what this is? That's a good old friend. It's the D'Alembert operator, right? The wave operator on Minkowski space. And another term which occurs is the trace of the h. So expressions of this type, h sigma tau. And let me write h for this without indices. So that's a trace of the h. And then our Ritchie tensor can be written in the following way. R lambda tau becomes what? Oops, no, I'm not that large. Okay, so the first term, I have a 1/2 in front of everything. Or let me write 2 times r lambda tau, that's more convenient. So in here, this index mu is raised. So I have d lambda, d rho, h. The mu is raised, become a rho tau. That's the first term. The second term is d lambda, d tau. And then I get the trace of the h, right? Both indices are summed away. So this is this here. Then I have minus d lambda d mu. Minus d lambda d mu, and the rho is raised and becomes a mu, h mu tau. Here, d lambda, d rho d lambda. And the mu becomes a rho, h rho tau. Oops. rho tau minus d rho d tau. Rho d tau, and the mu is raised h rho lambda. And finally, the last one, there we have the D'Alembert operator. D'Alembert operator h lambda tau. And I think this is not correct. Let me see. These two terms cancel, right? Anything else? No, I don't think so. Let me check. I think it's still not correct. Where are we? Here's our plus, minus. Oh, lo and behold, it is correct. Very good. Okay, so this was the Ricci tensor. Then we need the scalar curvature. So let's calculate 2r, because that's convenient. Then we have to multiply this with g lambda tau. And because this is already of first order, every term comes with an h, it suffices if I take the leading order term here. So, sorry, that's an equality sign. So I have r lambda tau plus eta lambda tau, and then the higher order terms which we neglect. So let's insert this expression from the line above. What do we get then? So we get 2r lambda tau is this here. So I get everything transvected with eta lambda tau. So I get eta lambda tau d lambda d tau h minus eta lambda tau d lambda d mu h mu tau minus eta lambda tau d rho d tau h rho lambda plus eta lambda tau D'Alembert operator h lambda tau. So now let's see. That's the D'Alembert operator, right? Here the index tau is raised and becomes a lambda. D lambda, d mu, h mu lambda. Here I have minus, the lambda is raised and becomes tau. And the last term, this is short enough so that I can squeeze it here. Well, I can, of course, pull the eta under the derivative, right, because it's constant, and then I get just a trace of the h. So I get what? I get 2 times the, so I have calculated 2r, and I found that it is 2 times box h minus, that's the same expression, right? Do you see this? Okay. Here I can change the index lambda into rho. I can just give a new name to the summation index, right? And here I can give a new name to the index tau and call this mu, h rho mu. And now you see that it is the same because partial derivatives commute and h is symmetric. Yeah? So it's really the same. So I get 2 times, it was, here the line ends, 2 times d lambda d mu h mu lambda. So the 2's go away and I end up with this. So I've calculated everything I need for the left-hand side of Einstein's field equation. Oops. So the field equation becomes, so I should, for the sake of precision, I should say, so the Einstein field equation without cosmological constant. Well, for gravitational waves which arrive here at the Earth, cosmological considerations are usually considered irrelevant. So we usually discuss gravitational waves in terms of field equation without the cosmological constant. Without cosmological constant. So what was the field equation? This was r mu nu minus r half g mu nu is, I just wrote kappa. This was Einstein's gravitational constant, which is 8 pi g over c to the 4. So I have in our approximation scheme, we have seen, I forgot the h here. That's of course nonsense. So we see that all expressions come with an h. So they are first order. So if I multiply this with a metric, I need only the eta. So I can write this in the form 2r mu nu minus r eta mu nu is kappa tau mu nu to within our approximations. And then I readjust the expressions we have found here. So, okay, now I have mu and nu. So lambda becomes mu, tau becomes, that's bad. Let me write here lambda tau. Then I can just copy it from the other expression. So 2r lambda tau is this here. D lambda d tau h minus d lambda d mu h mu tau minus d rho d tau h rho lambda plus box h lambda tau. And then minus r times eta. So minus eta lambda tau times this expression, box h minus d lambda d mu h mu lambda. Then on the right hand side I have kappa t mu nu. 2 times kappa. I multiplied with 2 here. I forgot this. So you would get 16 pi gc to the 4. So that's the funny thing that in the linearized field equation you have, if you use this expression, you have 16 pi times g. And in the ordinary, in the full equation without the linearization, you have 8 pi g. So, okay, so that's the linearized field equation. Well, it looks longer than the original field equation, but actually it's much easier to solve because it's a linear equation, right? So it's really a simplified equation. And we can even simplify it further by making a substitution. We have written it in terms of the variable h. H is now our field, which describes gravity, right? Gravity viewed as a field on Minkowski space, as a perturbation of the space-time of special relativity. We can substitute it by another expression, and then this equation will become even simpler. So we introduce something which is usually denoted gamma mu nu, which is h mu nu minus, I think. Gamma mu nu h minus h, what? Yeah, minus h half. H half eta mu nu. So if it is justified to linearize with respect to h, then it's also justified to linearize with gamma and vice versa, right? Because they are linearly related. So they are of the same order. And if we substitute this, then in fact this equation will become simpler. So let's work this out. So I want to substitute for h, so I have to solve this for the h mu nu's, right? So the first thing I need to know is what's the trace of this, because I have to substitute for the h. So I introduce gamma without indices as eta mu nu h mu nu. And from this expression I find that this is eta mu nu, okay, I write it in full. So in the beginning we have, no, what am I doing? Nonsense. what's, that's why I was confused. So that, of course, I want to introduce, the trace of gamma, and then I insert for gamma. So then I get eta mu nu h mu nu minus h half eta mu nu eta mu nu. So this gives what? This is just what we called h, and then I have minus h half, and this should have indices down, of course. That's a trace of the Kronecker, right? So this is the dimension of the space, and we are in a 4-dimensional space. So that's 4. So that's h minus 2h, so that's minus h, right? And if we insert this, so if we replace h by minus gamma, then we can solve this for h mu nu. Oops. So we have h mu nu is gamma mu nu. If I take this to the other side, it becomes plus 1/2 eta mu nu. And h is minus gamma, so it becomes minus gamma half eta mu nu. So that's the expression we have to insert. So let's call this field equation here star. So if we insert this into star, then we get the field equation in terms of gamma, and we will see that it looks nicer than in terms of h. So we get what? D lambda, d tau, h, and h is now minus gamma. Then minus d lambda d mu, d lambda d mu, and h mu tau is this here. It's gamma mu tau plus, let me write it this way, minus 1/2 gamma half eta mu tau. I could also write a Kronecker for this. Yeah, that's the same as Kronecker. The mixed components of the eta are the Kroneckers. Then I have minus d rho d tau gamma rho lambda minus gamma half eta rho lambda plus box gamma lambda tau minus gamma half eta lambda tau minus eta lambda tau box h, which is minus box gamma, minus d lambda d mu, gamma mu lambda minus gamma half eta mu lambda, and the bracket closed. So let's see. And the whole thing is 2 kappa t mu nu. So can we sort this already a little bit? Let me see, d lambda d tau. You see immediately that something goes away. Maybe that's too quick. Maybe I should do it step by step. So we have minus d lambda d tau gamma minus d lambda d mu gamma mu tau minus, this is constant, and it pulls the index mu, it pulls the index mu down to a tau. So I get d lambda d tau d lambda d tau gamma half, 1/2. So that's the first line, and the second line, minus d rho d tau gamma rho lambda plus the eta makes a rho into a lambda, d lambda d tau gamma with a factor 1/2. Then this here plus box gamma lambda tau minus eta lambda tau with a factor 1/2 box gamma plus eta lambda tau box gamma plus I have again used an index twice. Look, gamma is used up already, so I can give any name to the summation index, but not lambda. So let's call it rho. So I have an eta, where was I here, I think? Eta lambda tau, d rho, d mu, gamma mu rho. And the last one is plus 1/2. So rho mu, this gives a box, right? This gives a box eta lambda tau box gamma. So we see, I have made a sign mistake. The lambda tau, or do I? I think the terms with box gamma go out. This would mean that I've made a sign mistake. Plus something is wrong. So these three terms should cancel. To see they would if one of the signs would be different, right? Very bad. And another term should go away. D mu, this term here, lambda tau, where do I have this again? It comes with minus 1/2. And here this plus, this again doesn't go away. So this should be a plus. Lambda. Well, it is a plus. It is a plus. I just made a writing mistake, and then they do go away. That's fine. Let's see what about the box terms. Minus 1/2. Where does this come from? That's this here, right? Oh, this is a minus. This is a plus. And the last one is a minus, minus, minus. So I have three minus signs, and then they do go away, right? So they do go away. So that's our field equation in terms of gamma. Let's call this double star. So you see it's already nicer. So we have, how many terms do we have? 1, 2, 3, 4 terms on the left-hand side only. And we can even further simplify it, and then it becomes really nice. Namely, we see all terms on the left-hand side with the exception of this here, with the exception of the term with the wave operator, involve a divergence of the gammas. And actually I will now show that these terms can be killed when we use our freedom of making coordinate transformations. Yeah, we have not yet fixed the coordinate system uniquely. We are free to make coordinate systems of this form, and we will use this now. And then we will, maybe I should leave this and erase this here. Oh, that's better. Oops. It already looks like a sort of wave equation, right? But it has three ugly terms in addition. It's not yet just a wave equation, but we can make it into the wave equation by using the freedom of changing the coordinates. Okay, so if you look at this expression here at the bottom. No, here. Oops. On the left-hand side of the field equation. Here, these terms. These terms. All of them involve a divergence of the gammas. Yeah, where you have a derivative acting on the gammas and then a summation over a pair of indices. You have here the rho, I can interchange them, right? So rho acts as a derivative, and here's a mu. Partial mu acts as a derivative. So three terms on the right-hand side. On the left-hand side, sorry. Can't distinguish left and right. On the left-hand side contain something of this form. Yeah? What we would call the divergence of gamma mu rho. This can be transformed to 0. So I claim, and then I prove it, oops, where are we? Yep. By coordinate transformation. Well, of this form, which is still allowed, actually of the special form where these terms are not there, where we have just x nu plus, where we just choose the identity for the lambda and the 0 for the shift of the origin. And we have only this here, coordinate travel of the form x mu goes in x mu plus f mu of x with f mu small of first order, meaning linear in the h's or equivalently in the gammas. And of course, we have to prove this. How do we do this? Well, in order to work this out, we need to know how under such a coordinate transformation the gamma behaves. And to begin with, we check what the g's do, the g mu nus. Then we find what the h's do, and from that what the gammas do. So under such a transformation, obviously dx mu goes in, oh sorry, that's a straight d, dx mu plus d rho f mu dx rho, yeah, with a chain rule. So I just apply the differential operator d. Remember, this was a well-defined operator which acts on functions and makes them into covectors. So that's what we get from the chain rule. And I claim that that's obvious, right? We just differentiate this. What I write now is not quite obvious, but I will prove it in a minute. I claim that the basis vectors, the derivative vectors, transform in a similar fashion with a minus sign here, d sigma f rho d rho. And I think this I have to prove because it's not obvious. So what I have to prove is that this is dual to this here. If I insert this into this expression, that I get the Kronecker, right? That's the relation between the basis covector fields and the basis vector fields. If I apply this to this, I get Kronecker, delta sigma mu. And if the transformation formula is correct, then the same must hold on the right-hand side. So I have to apply this here, dx rho, onto this vector field, sigma minus d sigma f rho d rho. And if everything is correct, we should get the Kronecker. Let me see. If I apply this to this, of course I get Kronecker. So this is delta mu sigma. If I apply this to this here, I get minus d sigma f rho Kronecker. If if I apply this to this, I get plus d rho f mu delta rho sigma. And this term is of second order, so we neglect it. And yeah, you see that's the same term, right? The mu becomes a rho, and here's a rho. Oh, why is this a sigma? Oh, yes, it is correct. So I get delta mu sigma minus the rho becomes a mu, the sigma f mu, and here the rho becomes a sigma, delta sigma f mu, and this is delta mu sigma, of course. So that's a proof, okay? So that's the transformation behavior of the basis vector fields. And now we have to calculate, with the help of these expressions, we have to calculate, well, our final goal is to find out how the gammas transform. Yeah, because we want to make this into 0. So we want to choose the f's in such a way that this expression in the new coordinates becomes 0. So we know how this transforms. We have just calculated it. We need to know how this transforms. And where the gammas are constructed from the h's, and the h's are constructed from the g's. So we begin with the g's. So then, how do the g's transform? The g mu nus. Well, what are the g mu nus? They are this here, right? They are this here. So I see how it transforms. If I make a coordinate transformation, this becomes d mu minus d mu f rho d rho, d mu minus d mu f sigma d sigma. And if we multiply this out, this gives g mu nu. And this becomes minus d mu f sigma g mu sigma. This here becomes minus d mu f rho g rho nu, and the rest is quadratic in the f, so we neglect it. So we see, yeah, that's the transformation behavior of the g's, and actually we know already that if we just take the lowest order terms, then we have that this is eta mu sigma. Yeah, and then we get the term where two f's come together, where an f comes with an h together. So both are of higher order, so we neglect them. And here I have d mu f rho eta rho nu plus terms which we neglect. So that's the transformation behavior of the g's. So then we can calculate how the h's transform. The h's were g mu nu minus eta mu nu, right? G mu nu was eta mu nu plus, h mu nu plus eta mu nu. So this transforms into g mu nu. We have calculated what it does. So this g mu nu minus d nu f sigma eta mu sigma minus d mu f rho eta rho nu minus eta mu nu. And here I get again my h. So this is h mu nu minus d nu f sigma eta mu sigma minus d mu f rho eta rho nu. Okay, and our final goal was we wanted to calculate how the gammas transform. Well, for this we also need the trace of the h. So h, if I take the trace of this expression, I find that this goes into h minus d nu f sigma eta mu sigma eta mu nu minus d mu f rho eta rho nu eta mu nu. Yeah, I multiply everything with eta mu nu with upper indices, and I get, this is h minus, this gives a chronic nu sigma, right? D nu f nu And this gives the conic rho mu minus d rho f rho. And that's of course the same thing. So this is h minus 2 times d nu f nu. Okay, and now I should leave this. Now we get the transformation behavior of the gammas. And then we see that we can indeed make this divergence term equal to 0. And then we have found the standard form of the linearized Einstein field equation. Okay. So we wanted to know how the gammas transform. The gammas were h mu nu minus h half eta mu nu. So we know how this transforms and how this transforms. So I just look it up there. H mu nu becomes this here. H mu nu minus d nu f sigma eta. Actually, I could pull the index sigma, right? Why did I write this in such a complicated form? So the eta pulls the sigma down, it becomes mu. And with the second term, the rho is pulled down, it becomes a nu minus d mu f nu. That's much shorter. And then I have minus 1/2 eta mu nu times h. And h is here. H transforms into h minus 2 d, not nu, f rho. Okay, I think I cannot do anything with this. So that's, oh, I can do something with this. I can read that here again I get my gamma, right? So it transforms into gamma mu nu plus what? Minus d nu f mu minus d mu f mu. And then minus and minus gives plus. The factors of 2 cancel. And I get plus eta mu nu d rho f rho. So that's the transformation. And what I was actually interested in was this here. Oops. Gamma mu nu. So this transforms now into, well, here's the transformation behavior of the partial derivative into partial mu minus partial mu f rho d rho. Applied to gamma mu nu transforms into this. Gamma mu nu minus d nu f mu minus d mu f nu plus eta mu nu d rho f rho. So you see, these terms are all already of first order. So this is another first order term. So this gives something quadratic, which I don't write, right? And so I get this transforms into partial mu gamma mu nu. Then this here minus d mu d nu f mu minus d mu d mu f nu plus, where the eta pulls the index down, partial nu d rho f rho. And yeah, these two terms cancel. You see, partial derivatives commute. Well, here's an index pulled, but the index is pulled with an eta. Eta is constant, right? So it doesn't matter if I have this under derivative or not. So I can interchange these two indices. And then I see that these two terms cancel each other. So I see this expression transforms into this here. So now is the question, can I choose my f in such a way? Well, we made a coordinate transformation. There it was. And it was our goal, with the help of this coordinate transformation, to make this into 0. So there we see it becomes this here. So the question is, can we choose the f in such a way that this becomes 0? So if we choose f nu such that this expression becomes 0, so this means that box f nu, yeah, that's a box operator here, is d mu gamma mu nu, then we have in fact d mu gamma mu nu transformed to 0. The question is, can I choose my f in this way? So the question is, given any gamma mu nu, I don't know what it was in my old coordinates, can I find an f nu so that this equation holds? And the answer is yes. Actually, you know this in electrodynamics. That's a key problem in electrodynamics. So for instance, when you derive the retarded potentials, maybe you remember how this works in electrodynamics. You solve exactly this equation. You have a given source here. That's the electromagnetic current in the case of electrodynamics. But anyway, it's a quantity with one index, whatever the physical meaning is. And you want to find a potential so that this equation holds. And the solution can be written as an integral. That's what we call the retarded potentials. So that's the particular solution of this expression. So such a solution, so this choice is possible, as one knows from electrodynamics. For instance, choose retarded potentials. There are other solutions. The solution is not unique. So you can really write the solution as an integral over this expression. That's what we call the retarded potential. So this is possible. Actually, we will work with this solution in the next lecture. So I will write the retarded potentials explicitly for those of you who have maybe forgotten what these are. So at the moment, it suffices to know that such a solution exists. So we do this now, and then we have transformed. So we make a coordinate transformation. So our coordinates are now even more restricted than they were before. And in this restricted class now, we have transformed these expressions to 0. And then let's see what the field equation does. Then the field equation in the version for the gamma, that's what I call double star, then this reads, well, becomes very, very simple. Here it was. So let's see. We have transformed this to 0. We have transformed this to 0. Yeah, I can interchange the partial derivatives. Then the rho acts on this here. We have transformed this to 0. Here, again, the 0 term. So the only term on the left-hand side is a wave operator acting on gamma lambda tau. Oops, gamma lambda tau. And on the right-hand side, I have 2 kappa T mu nu. And that's what one usually calls the linearized field equation. One has to say that the gammas are now restricted by this condition that gamma lambda tau is 0. And now if you look at these equations, this looks very similar to what you know from electrodynamics, right? Think of the electromagnetic potentials. They also satisfy a wave equation of exactly this form. The difference is they have only one index. Here we have a quantity with 2 indices. Yeah? But otherwise the equation looks precisely the same. And we also must impose a certain additional condition on the potentials in order that the wave equation is satisfied. In electrodynamics we call this a Lorentz gauge. Yeah? This is analogous to the Lorentz gauge, and this is analogous to the wave equation for the electromagnetic potentials. So here in the gravitational theory, one calls this the Hilbert gauge, because David Hilbert was the first to suggest that restricting the gammas in this form. So the name gauge, of course, comes from the analogy to electrodynamics. Yeah? It is just because this is analogous to what we know from electrodynamics. Let me make this more explicit. Analogy to electrodynamics. And by electrodynamics now I mean electrodynamics in the standard form on flat space, on Minkowski space time, with no medium. So we have here the linearized Einstein theory. And we have here Maxwell theory. Here we have written our field equation in terms of these quantities gamma, mu, nu. In the Maxwell theory, we write analogous equations in terms of the vector potential, A mu. Yeah, the vector potential is analogous to the gamma, mu, nu's. Here we have a source, the energy momentum tensor. So what's the source in the case of electrodynamics? What do we have on the right-hand side in the electrodynamic case? What's the source of this?
For the wave.
For instance, for a wave, yeah.
Fluctuating electric charge?
Yes, yes. Well, actually, it is not just the scalar charge. That's part of it. It's a four-vector current. Yeah. So one component, the temporal component, is the charge density, and the other 3 components are the spatial current of the source. And the whole thing, the 4-vector, is called the 4-vector current, denoted J. Actually, we talked about this equation here. We in one of the worksheets, we had the analogous equation to this under discussion, where we saw that you get the wave equation of this form for the potential if you impose the Lorentz gauge condition for the potential. So here we have the Hilbert gauge. The Hilbert gauge, so that's this equation, partial lambda, gamma lambda tau 0. And here we have the Lorentz gauge. That's the Lorentz without T. Ludwig Lorentz, a Danish physicist, who's not so well known. The other one with a T is much more famous. He's a Nobel Prize winner. Hendrik Lorentz, he was Dutch. This is d lambda, a lambda 0, right? It's exactly the same equation, just with the difference that in the electrodynamical case we have quantities with only one index. And the wave equation, where we have written it up there, this is this here, gamma lambda tau is 2 kappa t lambda tau. Oh, I mixed up the indices again. Should be the same pair of indices on both sides, of course. And yeah, here is a equation for the potential. There was this funny dimensional factor. I think it's 1 over mu naught. Let me check it. Mu naught is this permeability of the vacuum, right? Yes, 1 over mu naught. So that's the wave equation for the potential, right? An arbitrary potential doesn't satisfy this wave equation. We have to impose a Lorentz gauge condition. Yeah? Otherwise, there's an additional term. We did this in one of the worksheets. So that's the analogy. Okay, and this was a brief overview of the linearized theory. And we will now talk about particular solutions to this, namely wave-like solutions. Now it's clear that the theory has wave-like solutions, right? We have arrived at the wave equation that's formally completely analogous to electrodynamics. And I should also, for later purpose, I should write to what extent the coordinates are restricted. So coordinates are now fixed up to transformations of the following form, well, we had transformations in the beginning. We had transformations of the following form at our disposal. X mu tilde was a mu plus lambda mu nu x nu plus f mu x, where the f mu's were small of first order. And now we have imposed the additional condition that we want to have the Hilbert gauge. And now let's see to what extent does this restrict the transformations. We can still make transformations of this form, but not with arbitrary f's. The f's now have to satisfy a differential equation. Namely, let's assume we are on the Hilbert gauge, and we want to preserve the Hilbert gauge. Then we can use this transformation here. So we are on the Hilbert gauge. So this is 0 in the coordinates in which we are working with. Is it possible to make a transformation so that in the new coordinates this expression is still 0? Yes, obviously that is true if this here is 0, right? So we are still free to make transformations where the wave operator applied to f nu is 0. So in addition to the conditions we had before, we must now require that f mu is 0. So we have still the freedom to make transformations of this form. It's quite analogous to the Lorentz gauge. If you're on the Lorentz gauge, you're also still free to make gauge transformations. And the gauge transformations are restricted by precisely this equation, where you have a scalar instead of the thing with one index. Yeah? The gauge function in electrodynamics is just a scalar function. So that's a transformation we have still at our disposal, and we will use them in the following. So let's sum up. We are now in a theory where the basic field equation is this here. Within this linearized formalism, this is the field equation now. And we have to be careful that we have this additional condition on the gammas. And well, we do now exactly the same thing that one does in electrodynamics. We study wave-like solutions of this. So there are two aspects which are usually studied one after the other. The first aspect is as you look at the homogeneous equation. So we ask how waves travel outside of the sources. If you're in the region where the sources are not present. So there are your sources, and I'm observing the wave here where I have vacuum. So that's the first question I study. And we will find that they have plane harmonic wave solutions as in the electrodynamic case, and we will study the polarization states for them, which are a bit different than for electromagnetic waves because now we have two indices. And then the second question will be, how are the solutions related to sources? So what kind of sources will produce a certain sort of waves? And this will lead us to Einstein's famous quadrupole formula. So that's the two things which we will do now in the next 2 hours or so. So the first thing will be section 7.2. We will now study plane harmonic wave solutions. Of the linearized vacuum equation. So where I have the 0 here on the right-hand side. Linearized vacuum field equation. So the equation we are studying are now this here. Yeah. And of course we have the Hilbert gauge. Well, and for each component, this is just the ordinary wave equation, which you have studied in, I don't know, in your first year or in your second year. So everything you have learned about the solutions can be taken over from there. So we know that plane harmonic waves are solutions of this. And because of the linearity, we can build more complicated solutions by the superposition principle. So by adding plane harmonic waves together. By the way, that's the physical meaning of the plane harmonic waves. Everybody knows that plane harmonic waves do exist in nature. Yeah? The plane harmonic waves comes from infinity, extends to infinity, and goes out to infinity again. Of course, such a thing exists in nature. Realistic processes, they are created by a source at a certain time, then they oscillate for a while, and then they die down again. But solutions of this sort, which go up and then down again, can be written as a Fourier integral. So they can be decomposed in terms of plane harmonic waves. And that's the physical meaning of plane harmonic waves. You can any reasonable physical wave write as a superposition of plane harmonic waves in a linear theory, not in a nonlinear theory. But here in a linear theory, this works. And we do exactly the same thing now. So we consider plane harmonic wave solutions. So what is this? So what's the general form of a plane harmonic wave? So we have functions gamma, mu, nu, which of course depend on x. And a plane harmonic wave is the following. It is usually written in complex forms. This is just a compact and convenient way of writing it. So we have an amplitude, which must now have two indices, a, mu, nu. In the case of electrodynamics, it has only one index. And then an exponential form with a typical phase factor. So this is, if you write it out in spatial and temporal term, this gives frequency times time minus spatial wave vector times spatial position vector. Yeah, so that's the usual phase factor written in 4-vector notation. We have done this for electrodynamics a few weeks ago. So hopefully everybody remembers how this works for electrodynamics, where this is the electromagnetic potential, and it looks like that. Yeah? Exactly the same thing. And now we will see where, also I should mention this, where k rho, where the k rho I should write are real, and the a mu nus are complex. Yeah, this is just a convenient way of writing a combination of plane harmonic waves with arbitrary phases in a compact form. So you could write this out with the help of sine and cosine in purely real form, but then it becomes longer, and the calculation is easier if you do it in this way. By the way, that's also something which only works for with linear theories, right? Because what we will now do is we will take the differential operator under the real part. And if you have a nonlinear differential operator, you cannot pull it under the real part. Yeah? So this whole complex business doesn't work for nonlinear wave theories. You will never write something in the nonlinear theory in this form, in this complex form, if you want to describe a field which actually is real, which is really measurable. In quantum mechanics, actually, the wave function is complex. Yeah? Then, of course, you do use this. If you use Schrödinger theory or nonlinear modification of the Schrödinger theory. But if you are dealing with something which is really measurable, which should be real, then this notation doesn't work. Okay, so we will insert this ansatz now into the wave equation, and we will see what's the, it is a wave equation, into the field equation, and it will tell us how the k's and the amplitude should be related. So k rho is the propagation wave covector, and the a mu nus are the amplitudes. And of course, they are not free. You know this from electrodynamics, right? You know that there are certain transversality conditions which must be satisfied. And then you get restrictions on the polarization states. And we will do now the analogous thing for the gravitational waves. Oops. So we have two conditions on the amplitude and the wave covector. One comes from inserting this ansatz into the field equation. The other comes from inserting this ansatz into the Hilbert gauge condition, which of course also restricts the amplitude and the wave covector. So let's begin with the Hilbert gauge condition. inserting into H. Have I introduced the name? No, I think I haven't yet. So let me write it out into the Hilbert gauge condition. So I want to have 0 is partial mu gamma mu nu. Just to remind you, this, the indices are pulled with eta. So if you write this more explicitly, then it is this here. If you really want to calculate the derivative, then of course you should pull down the index because only this is the ordinary derivative operator, right? So we insert this expression now for gamma. So this is eta mu rho d rho applied to the real part of a mu nu e to the I k rho x rho. Okay, and this is what? This, well, everything is real, so I can pull this under the real part. And I have eta mu rho partial rho, where the a mu nu's are constant. And then I have the operator acting on e to the I k rho x rho. Again, I have used an index 3 times, right? Here, that's the derivative index is called rho, so I cannot call the summation index rho. Sorry for this. X, let's call this sigma. Do I have a sigma? No, fortunately not. So, and this, of course, can easily be calculated. So this is a real part of, I could use this in order to raise the index, just for making the expressions a bit shorter. And the derivatives gives I. If I differentiate with respect to x rho, so I get I times k rho, right? I times k rho, and the exponential function reproduces itself. So that's the derivative. And this is supposed to be 0 for all x. And this holds for all x only if the coefficient is 0. Yeah? Why is this true? Because, well, if you write it out in cosine and sine, you see you get a linear combination with constant coefficients of a sine function and a cosine function. And the sine function and the cosine function are linearly independent. Yeah? You cannot add the sine function to a cosine function with constant factors in a way that you get the 0 out of it. Yeah? So they are really linearly independent. That's a standard trick which you always use if you work with this complex notation. When you have an expression of this sort, you know immediately that the prefactor of this expression must be 0. You convince yourself once of this and then you use it for the rest of your life. So this can only hold if this factor is 0. So the I is definitely not 0. So it holds only if, let me write it in an extra line. Here maybe it's, it doesn't matter. Rho nu k rho is 0. So that's our first condition. That's again quite similar to what we know from electrodynamics. In electrodynamics, we don't have the second index. That's the amplitude of the electromagnetic potential. And in the Lorentz gauge, the propagation direction is perpendicular to this. Yeah, in the Lorentz gauge, the potential is perpendicular to the propagation direction. So that's quite, well, in space-time. These are space-time indices. So what I did with my fingers was not quite correct. Yeah? It's in the space-time up there with 4 indices. So you have the same orthogonality relation. So that's what comes from the Hilbert gauge. So that's the first restriction. Yeah, so the propagation direction and the amplitudes are not independent. They must be related by this property. And the second is, what do we get if we're inserting this into the field equation? Any guess? What do we get? What restriction on A, mu, nu, and or k rho? Would you expect something? I mean, you remember from electrodynamics. Is, apart from this gauge condition, does any of these two quantities has to satisfy some other condition? Or are they completely free? Is this a completely arbitrary 4 vector for electromagnetic waves? Can an electromagnetic wave propagate with any velocity? In vacuum, yeah, in vacuum. Yeah. Definitely not, right? I think everybody knows that electromagnetic waves in vacuum propagate with the speed c. And this restricts these things to light-like covectors. Yeah? So they must be light-like. They must describe a propagation at the speed of light. And actually we'll get exactly the same result for the gravitational waves. So in this linearized theory, where we describe everything as a perturbation on Minkowski space, also gravitational waves move at the speed of light c. And we will find this in a minute. So if I don't make a calculation on mistakes, this should come out. So the equation was this here, right? This was the field equation. And yeah, what was this? Let me just write it explicitly, d rho d sigma, right? And gamma mu nu was a real part of a mu nu e to the I k. I should use an index which I haven't used yet, so let's say tau, x tau. Okay, so what is this? That's easy to calculate. So the eta rho sigma can be pulled under the derivative. Then I have the rho. And then I apply the derivative operator in the direction of sigma. A mu nu is a constant. And if I differentiate this with respect to x sigma, I get a chi k sigma e to the a k tau x tau. So that's the first derivative operator evaluated. And then I can pull this over the a, which is constant, over the k, which is constant, and then it acts on this here. And I get, maybe I should use a new line. So I get, that's a real part of what eta rho sigma a mu nu I k sigma. And then d by dx rho applied to this here. This gives I k rho e to the I k tau x tau. No, that's a curly bracket. And now the same game. This is 0, and this can be true only if this coefficient is true. So this holds for all x. For all x tau. Only if this coefficient is 0. Well, the a mu nu, the amplitude, of course, should not be 0. Right? You want to have a wave with a non-zero amplitude. Yeah? The a mu nu's, these are constant amplitudes. So they do not depend on x. So clearly, this, if this is not identically 0, then this here paired with k sigma k rho must be 0. Holds for with a mu nu not identically 0. I mean, not all components are 0. Yeah, of course, some components may be 0. But at least one component of a mu nu should be non-zero, and then the rest must be 0. And that's precisely the condition I wanted to derive. K rho, k sigma is 0. This means k sigma is a light-like covector, right? So this means that gravitational waves, or I should emphasize, in this linearized theory, because this is definitely not true. It doesn't make sense in the full nonlinear theory. In this linearized theory, gravitational waves propagate at the speed of light. Yeah? And speed of light refers to the light cone of the background Minkowski spacetime. Yeah? We are in a theory where we have a background, which is just the spacetime of special relativity. Our gravitational field is a perturbation of this. It lives on this background spacetime. And in this linear approximation, these wave-like solutions propagate at the speed of light with respect to the background. So that's what is meant by the statements, which we have certainly heard before, that according to Einstein's theory, gravitational waves move at the speed of light. Yeah? It refers to this linear theory, and the speed of light is measured with respect to the background metric. Okay, we will further evaluate this on Thursday. So we have found now that electromagnetic waves have to satisfy these two conditions. And what we will do next time is we will count how many components of the amplitudes are actually independent. This will tell us how many independent polarization states there are. So what about electrodynamics? How many polarization states are in electrodynamics? So by independent polarization states, I mean that I can write any other polarization state as a linear combination of these two. Yeah? So usually you use left-handed and right-handed. Yeah? Or you use linear polarization in this direction and linear polarization in this direction. So either way, you write it with two basic states. You would expect here that here I have much more polarization states. Yeah? But as a surprise, maybe we will find that it's also only two. But the geometric interpretation is different. So it has nothing to do with a vector oscillating along a line or something like that. It will rather have something to do with a deformation in a plane perpendicular to the wave propagation. So this will give us these famous plus modes and cross modes of gravitational waves. We will discuss this on Wednesday. Okay, have a nice weekend.